Hello everyone, welcome all on DataFinix webinar. Today we will speak about data, about managing data, and how you can use new product from I can say pioneers in data versioning. Uh, uh, yeah, in, Iterative, guys from Iterative today will share their new product and how you can use DVCx for scale your dataset from Generative AI. Today with us, Tibor Mach. He is a machine learning solution engineer, and he will present today this topic. If you have question, please use Slanda. The link is in the chat and under the video, and we will answer for your question in the end of his presentation. For now, I give to Tibor microphone.
Okay, thank you for the introduction, Mitro. You should all be seeing my screen, hopefully. If not, then let me know in the chat.
Yeah, this one. Yeah.
Good. So let me maybe actually, before I start, really let me introduce myself. As Mitro mentioned, I'm a solutions engineer at Iterative. I'll introduce the company in a second. Before I was doing this, I was working in consulting. I spent 4 years doing that, starting as a data scientist, then slowly drifting more and more towards MLOps, and just managing the entire machine learning lifecycle rather than working on individual models. But starting as a data scientist and going there, I think it helped me kind of appreciate all of the aspects of ML. Before that, my background is actually not in computer science. It's in mathematics, probability theory. I was working as a postdoc for a bit, and then I moved into machine learning. So MLOps was really interesting to me, and that's why I joined Iterative, because I actually started learning and using DVC and other tools from Iterative before joining, because I really like the idea behind DVC. I like this new product DVCx as well, because it answers to a demand which is rising, I would say, right now, and also it's kind of adding the full picture to MLOps. So with DVC, I will also go through that a little bit. I will, for those who don't know DVC, I will give a bit of an introduction of that part of our products as well, and then I'll move to DVCx, which is the Gen AI LLM. It's not just for that. It's generally for managing large unstructured data. But of course, right now, all the hype is around LLMs, Gen AI. So this is also what we will kind of structure this around a bit. And there's a link, as you can see in this very simplistic picture, there's a link between DVCx and DVC. This is also why I want to mention DVC. But DVCx can make sense on its own as well. For certain use cases, it really depends on what you use it for. So let me just jump. Actually, let me just open the full slideshow. Or not, I don't know. It seems to be okay. Now it's working. Great. So let me just give you an overview of all the products that we have at Iterative. So as Mitro mentioned, we have DVCx. That's an upcoming product, I would say, rather than a new product. The release should be quite soon, probably in December. So you get a little bit of a preview today. Some things are still being worked on it, but it's very close to a released version. We have DVC, which is our first and I would say main product in a sense, or up till now at least. And then we have a SaaS offering, software as a service, kind of to wrap it all around. So if you think about these three things, it's DVCx is mostly for large data set, unstructured data, specifically creation of large data sets. And the X I mean, to me, it stands for not a new logo of Twitter, but extra large, basically. So you have large unstructured data. And when I say large, I mean millions of images, even billions of images. That kind of scale when you actually want to do the Gen AI models, or maybe you don't want to do Gen AI models, but you still want to curate large data sets like that. I will give an example of it's not an example of an actual customer, but it's very similar to an actual customer that we're kind of piloting DVCx with. And this might give you some ideas of the use cases that might be interesting. Once you kind of do this, in the scenario where you have large data sets, but then you want to train relatively small models, but perhaps on a curated data set. So you start with a lot of images, you need to filter some of those because you want to fine-tune your models further, and you want to use maybe something like reinforcement learning, or you want to really fine-tune a specific aspect of your model. You have a lot of data, but you need to kind of find the right data for your models to get even that little better. Now, or maybe a year ago or so, all the buzz was around data-centric AI. How curating data is really the most important thing right now. This is also something that DVCx can help you with, and then you can transition to something like DVC to go on. So DVC, you can think of, so while DVCx, you can think of it as something like Spark for unstructured data. It's a simplification, but I'll show you how that actually materializes. And DVC, you can think of it as something like Terraform for machine learning. So the whole point, or the main point of DVC, is to make it possible for your machine learning to use GitOps practices, to have Git as the single source of truth for all that you do in your machine learning, from the raw data for your models, all the way through the experimentation, all the way to a model registry, and assigning models to stages, to production, etc. So the same way that Terraform does this for infrastructure, DVC does this for machine learning. DVC is mostly free open source software. If you're a single developer, or if you have one or two projects, you probably are okay with just that. If you have a larger team, or if you have multiple projects, or if you have both, which is often the case, then it also is useful to use our software as a service offering, which will include DVCx, and which is called Studio. It's called DVC Studio. It has basically features for collaboration, for sharing experiments, live tracking, and sharing those experiments with your colleagues. It has all those bells and whistles of all the experiment trackers that you're used to, but it also stays focused on this GitOps approach. It still keeps Git as the single source of truth for everything, but it provides you with this environment that you can collaborate in easily, even with less technical users. It also now has more and more features which kind of help you manage credentials. So if you want to access models, you can do it through Studio. You don't have to share, for example, access keys to MS3 buckets or something like that. So I won't really talk too much about Studio. I will show it though, because DVCx runs in Studio. We will see an example of how DVCx works now. I will just go very briefly now through what DVC does, because it's kind of illustrative for what it can do and for where maybe it has some shortcomings which are addressed by DVCx for this particular scenario where you actually want to use those large data and then train some models on those. Just very briefly, all of this, as I mentioned, it kind of runs on your infrastructure if you work. That's pretty much true of all of those tools. You can use it on any of the major cloud providers. You can use it on-prem as well. Since this is very tightly coupled to Git, at least, especially with DVCx, with DVC, you can use it with any GitForge, GitLab, GitHub, Bitbucket. And while DVCx is mainly aimed at unstructured data, DVC is kind of agnostic in this sense. So you can really use it for structured data, unstructured data, anything really. if you work with big data which are structured, you would probably use something like Spark. If you have big data which are unstructured, which has been more and more common recently, then this is where DVCx comes in. All right, so let me move on, and let me just start with a brief intro of DVC. I'll give this maybe 10 minutes, and then I'll jump into DVCx with the context that we get from this. So DVC, yeah, that's our old. It's still obviously the main product, but it's the first thing that we created, maybe a flagship of sorts until now, at least. And the way it works is, as I mentioned, it kind of works like Terraform for data, but you can also think of it as being Git-like. So it's not replacing Git in any way, shape, or form. It's actually working together with Git. But it's kind of replicating the Git way of working with your data. So what it really does is, for example, let's say that you have a machine learning model. You have a ML project, you create a model, and it could be one of these transformer models which are quite large. So 500 megabytes is very, very possible for a model like that. It could be even more. So that's not something that you want to version with Git, right? So what do you do? What you would do normally, if you use something like SageMaker, maybe that's kind of handled by that. But then you're kind of fixed to that platform. Or you could just say, all right, I'll save my model to S3 or my NAS drive or anything, and I'll just save the path to that model in my Git repository in like a metadata file. And there you're getting a little bit closer to how DVC works, but it does some things on top of this because it kind of does the versioning for you. So there's no danger of people making mistakes. There's also what DVC does, it has its own cache, the same way Git does have a cache. And it versions that, it pushes that to a remote, which could be that S3 bucket, but it's managed by DVC. So you don't have to worry about rewriting that path to S3, or maybe if you're versioning a dataset, you don't have to worry about somebody deleting 100 images, and now that you're trying to reproduce your model with supposedly the same data, it gives different results and you don't know why. So this is kind of all handled by DVC. And since it works in a Git-like fashion, it basically looks up, it works with hashes the same way basically that Git does. So the effect of that mainly is that, first of all, everything is secure. You really know that it's that one file, and it doesn't duplicate anything. Once a file is versioned on the remote, even if you use 500 different commits, it's still going to refer to that single file. So this, again, makes it better in terms of reproducibility. And the connection to Git is through these metadata files that DVC creates automatically. And these are actually versioned by Git and stored in your Git commits, unlike the actual files. And these metadata files are the link that DVC uses to kind of pull the data from that remote locally. Now, this principle is then kind of propagated to machine learning pipelines. I won't have time to really talk about DVC pipelines today. But let me just say there's a quite a simple way to create pipelines with DVC, where you can structure the stages of your project, and it works again in a way that captures all the inputs and outputs of all the stages, and it versions them automatically, the same way that I just described with data, or the model that you would version manually. So here is an example. If you run a DVC pipeline, you end up with this log file, and as you can see here, I have the hashes of all the inputs of my stage data split here. The same goes for the outputs of those stages, and the same goes for all the stages. So in the end, what I end up with is a fully reproducible ML pipeline, which is versioned in my Git repo without having to actually version the data by Git, which is usually not a good idea for anything that's more than a few megabytes, really. Right. And also it has some other features that are cool about this. So for example, you can skip stages because you know that the outcome of a stage is going to be exactly the same in some situations because of all the versioning. I won't have time to go into that. Maybe if there are questions, I can briefly touch upon this. And then the third part of this is that the same is again applied. It's the same GitOps logic is applied to the model registry. So the model registry, which we have in that studio platform that I mentioned, it allows you to manage the lifecycle of your models once you register some experiments as actually versioned models. And all of the actions in that model registry are captured as Git tags. So in the end, they still live in your Git repository. You get the fully auditable history from there. And you are also, because of this, you're able to connect the model registry actions very easily to your CI/CD, because every action corresponds to a tag, and then it's a very easy step to, for example, write GitHub action workflows to deploy your models, for example, or build a Docker, or do anything really that you want. So that's kind of the philosophy behind DVC. That you can really apply GitOps at every step of the ML lifecycle, but there are some limitations of DVC, and one of the limitations is that DVC needs to work with your data on the machine where you're working to version it. So it stores the data in a cache. The cache is pushed to the remote. But this doesn't really work all that well. If it works okay if you have thousands, 10,000s, even hundreds of thousands. Let's say if we stay with images, it doesn't have to be images, but we're going to be mostly talking about images today. So let's say you have a few tens of thousands of images. It's okay. You can version it with DVC. You have direct access to it. It has a lot of advantages. But once you get to the scale of millions or even billions of images, this is no longer practical. You can't possibly have a machine where you can download all of that data. And even if you could, it would be expensive and slow. You need to work with data like that in a parallelized fashion. The same logic that applies to Spark. You don't want to use pandas if you have, let's say, banking transactions from your bank for the past 10 years. It's going to be terabytes of data that you just can't process locally. You want to process that in a parallelized fashion and maybe turn that into something smaller that you then use with your machine learning. And the same thing you can do with DVCx. So, and there's another aspect of this. So I think a lot of you have probably seen an image like this. So DVC, in many ways, is mostly helping you with the ML modeling, improving your algorithms, making sure they're reproducible and all of that. And that's important stuff, obviously, if you're trying to train a model. But if you have any practice with data science, you know that really, if we just go by time you spend working on something, most of the time is the boring stuff, but important stuff of cleaning the data. And if you work with something like CV models, a lot of that is also labeling, well, even with other contexts, but especially in CV. So then this is also something where DVCx is supposed to help, sort of with those 80% of time that you would otherwise spend working on anyway. The difference here is, okay, you can use tools. There are tools to help you label data. There's a labeling studio. There are, I don't know, I don't even probably know all of those tools. And the same goes for like data analysis, things like that. But the difference comes in now with these large data sets that are being used in Gen AI, LLMs, basically transformer models. That's what most of this ends up being. These are large models. They need a lot of data, and they can actually make use of a lot of data to get better. But that means that, for example, labeling becomes a challenge, because at this point, you could hire a lot of people, and let them label your data set. But if you have hundreds of millions or billions of images, it's going to be very costly to do this. And it's going to be very costly to make this in a consistent way. So there might be better ways to do this. One way could be to maybe just label a little bit manually, then create models that can actually do the labeling for you, and then use that in your data chain as an automated labeler, which is then going to be consumed by another model down the line. Or in fact, it could be the product itself. But you want to really label the entire data set if you have it. Otherwise, you're throwing away part of the data. That's your gold. That's why Facebook is for free mostly, because they really make so much money on that. And you want to make use of that too. But for this, you need scaling. So yeah, if you have unstructured data, you would probably use something like Spark in a lot of cases. For unstructured data, Spark is not all that great, and this is where DVC comes in, and I'll show you some examples in a moment. And this cleaning, that's another part of it. So basically, you want to query very, very large data sets. You want to add some signals to that data set, and you want to kind of bundle it up. What do I mean by bundling it up? So here is a anonymous website from the internet. You probably won't recognize. Yeah, okay, so it's Amazon. This is just a screenshot from a random website on Amazon, a random page on Amazon. So there's a vest, a woman's vest, and there's quite a lot of data here that, if you think about it, well, Amazon definitely is going to work with this. Amazon is not one of our customers, but we do have a customer we're piloting DVCx with, which is actually similar size, well, not similar, but yeah, it's roughly the same order as Amazon, and it's also an online retailer. And I'm not going to mention them exactly. I'm not going to mention the exact use case. So but it's going to be very similar to what I'm going to be describing here. So let's say that we have this eShop, or even aggregating many eShops, and we have these images of items, right? So the first problem we might have is we have images, we have structured data, like the fabric type, that could be a categorical variable maybe, or origin could maybe also be categorical. But we also have a lot of unstructured data. We have ratings, which are reviews, and they're completely freeform. We have these product descriptions, which are provided probably by the producer of the item or by the distributor. We also have other images. So, for example, images of the same product, maybe from different angles. How do we find which are which? And then we also would like to show our customers something that's related, that they might like if they like this product, right? So how do we go about that? So obviously there are many ways, and this has been done for a long time to varying degree of success. But now with those Gen AI tools and with those large models, you can actually do quite a bit more than in the past. So actually, in my previous job, we had a similar customer to Amazon, which was aggregating data from various stores. And one issue they had was making sure that they don't list the same item multiple times. So if you can buy it from several shops, they would want to kind of aggregate that and show all the shops you can buy it from. But that's actually quite difficult, because you can't just go by ID necessarily, because the IDs can be different. A lot of that is going to be wrong. So there are many ways that you can put it together. You can go by the item description, see if those are matching. You can do all of these things, but the best thing you can do is to do all of that at once, and also work with the image data and some kind of a similarity search between the product. But if you try to do all of that, it's going to lead to good results. But once you want to scale it up at a level of Amazon, or even something slightly more modest than Amazon, on a regional level, you're going to hit a lot of blockers if you don't have parallelization and concurrent and way to run all of these queries at scale. One other thing that you're going to run into is that you really need to manage all of those different data sets, and they kind of need to be put together. So for example, for this item, I would like to have a way to say, okay, so this is that image. It also has all these reviews attached to it. It also has this description, and it has these images which are similar. And I want to kind of keep it all tightly coupled because I want to use it as a single data set that I iterate upon. So that's one thing. And what I want to do with it, once I actually put all this information together, I might want to find similar stuff so I can actually recommend all of these other products. Or I can actually go with this way and just show sponsored stuff. That's another option. But even Amazon is just not showing random things. It's, even though some things might be promoted, they're clearly similar to the image of this item. So yeah, so you want to do that. You might also want to remove something. So for example, you might have by mistake some images of naked people that you don't want to show in your e-shop, or you might have some reviews which are spam or something that you really don't want to show. And maybe it's not just spam. Spam is easy to filter, but maybe it's something that's just unrelated to the product that you don't want to show. So you really still need the context of all of this other stuff related to the item if you decide whether to show it or not to show it. And once you do all of that, and you want to do that at scale, right? And once you do all of that, you want to version these data sets, at least if you want to use them somewhere for ML down the line, or for any really kind of auditability or reproducibility. Let's say that I use all of this information from all of my images, from all of my clothes that I have pictures of and descriptions of, and I train some models down the line. It could be a model like Fashion Clip, which I'm going to show in a moment, which kind of is used for finding similarity between combining unstructured textual and image information. But then a new collection comes in, the winter season, and I retrain the model on that new data, or including that new data. I want to be able to, again, go back and see that, okay, this is the data that actually were used to version this model, so that I can compare them between each other. You remember that the whole deal with DVC was to version everything, to really have completely reproducible pipelines. With DVCx, you don't want to lose it. So you need something like that as well, or with DVCx, with anything that you use for dataset curation. Yeah, all right. So that's kind of the motivation. That's what we want to get to. So let me just shoot. So this is a very high level picture, and then I'll jump into the UI of DVCx in a moment. So from the high level, you have some data, you store them on your local storage. You can have them in, or you can have them on S3, Azure, GCP, anything like that. As I mentioned, we're kind of agnostic here. And then what DVCx adds to it is a metadata layer, which kind of helps you work with that data without moving it anywhere. It just creates basically a metadata layer on top of it as sort of a data catalog, but a little bit more than that, because it allows you to add more information, to combine all of these different sources of information and add new signals, which is probably best explained if I show it in a second. And it also gives you a dataset manager, a UI where you can do all of these things, and you can also use it to automate all of these jobs once you're happy with the results. And then you publish the dataset, you export them either for any consumption of any algorithms down the line. It could be that you have some kind of a collaborative filter, for example, here to show these related products, or you actually go and train some models on top of those data downstream. So let me actually switch now to the actual UI. So let me just very briefly, so we don't have that much time, unfortunately, but let me very briefly show you where the UI comes from. So this is our studio platform. So normally it's actually, or so far it's been used for DVC projects, where you kind of import the repository of with your models. When you, as a project, when you open it, you can look at experiments, compare their metrics, all of that stuff that you see elsewhere. The differentiator mainly here is that everything is actually versioned in your Git repository in the end. Then you have a model registry where you can see all of the models. You can add stages to them. You can connect it to CI/CD, as I mentioned. You can go to individual models, but that's really not what we're going to look at today. About 2 weeks ago, I had a talk at an MLOps World Conference. I was talking just about DVC for 90 minutes, and I still couldn't cover everything. So here we are very, very brief. But there's the third bit, and that's the DVCx. So here we have a demo team. So you're actually in Studio, you're organized in teams. So for example, you can be a part of several teams. Here I actually have the DVCx platform under the datasets tab. And if I open it, you can probably immediately recognize this as reminiscent of some of these like SQL managers. And that's actually not a coincidence. This is supposed to mirror that approach. This is supposed to be for data preparation, exploration, but you then create maybe cron jobs or automation that kind of versions and curates those data sets for you. But you start with doing that manually, exploring what you actually want to do, how you actually want to curate, and you start with data sources. So here we have an S3 bucket, and as we saw in that image just a moment ago, it can be also Azure, it can be local storage, anything. But here we have an S3 account. On that S3 account, we have multiple buckets. Each of those buckets contains a data set. We have some example data sets here, which are used for demoing. For example, we have the Lion data set, which I'm going to use now. The first thing that you want to do is to index the data set. What it does is it actually retrieves the information from that storage. So for example, from AWS here, from S3, it gives you some basic metadata information, and it creates a table, or it makes it available for DVCx to work with. So I can just create an index here. I could also pair JSON pairs between, for example, images and masks. I'll actually do it in a different way that I'll show you in a second. So let me just create an index. So yeah, now it's indexing, which means that in a while, I think it's going to be about 20 seconds or something, we're going to have the dataset, the bucket indexed, and then we can start working with it in this kind of a SQL-like or Spark-like fashion. What we use here is a library called DQL. So DQL kind of sounds like SQL. It sounds like it's a language. It's not a language, actually. It's a Python library. So you don't have to learn a new language. You can just work with Python. But otherwise, it has a lot of methods and functions which are similar to how you would do things with SQL. So, for example, you can run some basic operations like filtering your data sets by name, size, etc. But you can add a lot more, actually. So this is why I'm here in the JSON pairs. And what you can do with it is, okay, so this indexing is taking a bit longer than usual. It's maybe because I'm actually now restricted to a single machine. Normally, we would work with a cluster of machines. Right now, I'm on a single machine, so things are a bit slower. But once this is indexed, maybe I just need to refresh it. Once this is indexed, it's available for you to work with, and you can run a query like this. So, if we look at this, basically, I just mentioned the bucket. I do some filtering, and here's the interesting part, actually, where I add signals. I have some JSONs which are related to my images, and I want to pair them. So I want to create essentially a metadata layer on top of my data set of images, where I have all the information, not just about the images themselves, but also the stuff that's related to all of those JSONs that are attached to this. So this is actually, if I run this query, and I did that today, so you already see the results or the preview of the results here, then you get something like this. You have this metadata layer on top of the images. So we have like 50,000 images here. Here we see the first 20. we can look at some of those images. Yeah, so this is a lion data set, so it contains actually quite a lot of different images. It's not all that specific. Some of those are quotes. It gives you all the information that you would get from indexing the data set. It also gives now the information that we got from these JSON pairs. So from the JSON files that were attached to those images. And we can actually do more than this. We can write our own UDFs, and we can add new signals using machine learning models. This is what I was hinting at with the auto labeling at the beginning. But let me actually, before I show you that, let me actually refresh and see if somehow the indexing finished. So this is the bane of live demos of things which are not released yet. But fortunately, we don't have to actually worry about this right now because I ran this already, and the results are here. Here's the preview. But if I now wanted to actually persist this data set with those JSON pairs, I would just click here on register data set. I would give it a name. I don't know, what is this? Lion with JSON. And it starts versioning automatically. So it's offering the first version. I could rename it to something else, and you can add some tags and descriptions. So I'm not going to do that now. Then I just click on register dataset, and it's going to create that dataset for me. And as you can see here on the left now in the datasets, it showed up, and we now have a first version of this dataset. We could then export it. This is actually not shown here, but it's in the development version right now, where I can export a data set, which is where I can then use it with, for example, with DVC or something else. Oh, now it looks like the indexing finished finally. So I could use it downstream for training ML models, right? So here, what I achieved is I took all the large data set. I just picked the JPEG files from that. I added all the JSON information from the JSON files. I packed it in a single table that can be then used by anything downstream to reference all of those images. And I packed it as a dataset. And the dataset is really nothing else than a table with references that I can use elsewhere. But the references include all these extra signals, all this extra information that I got from the JSONs. Now, JSONs are nice, but I want more. And what I want is, I mentioned fashion clip, right? So this goes back to that image that we had where we took the actual image, we took some textual description, we want to combine it together. We want to use, I don't know if you know the clip model. It basically, it's a way to kind of work with unstructured data together with text and with images at the same time and produce some interesting results. In this case, we're just using an F-clip score, and we can be using it to find similarity between images. So for example, when I want those vests which look very similar, then I can use the F-clip. But again, in this case, I want to run it at scale. I want to run it on my entire data set. And this will be possible here because I can run this in a cluster. Like I mentioned, right now I'm on a single machine, but you can in DVCx set up a cluster, 8, 10, 20 machines, and these can even be GPU machines, making it even quicker, and I can add signals to that. So I can take that data set that I just created. In fact, this is a different data set, but it doesn't matter too much. This is a data set from Zalando. That's a European, I think it's a German clothes shop. And and I can add this fashion clip score to it, so that now I have a data set which not only has all of those informations, all of that information, but also this F-clip score. So I can then maybe use it downstream for some machine learning or for collaborative filter, for example. All right, so then again, I would run this query. I'm not going to do that because it's not going to create anything else than what's already here. Then I can again register this data set as something new. So in fact, I think this was registered. Oh, it wasn't. So I could create a new data set, or I could actually Yeah, I think it was registered. I think it was the Leon JSON. So I can actually add a new version of that data set. I already have 11 versions here apparently. So I can create a 12th version. Yeah, why not? And again, all of this stuff is version. I can always look up I can also look up the query that created the data set. And I can, of course, look at the results or export the results. So how does this work? Why do I have fashion clip? This is because DVCx enables you to use UDFs. You can import them in the settings where you can just specify, the requirements. But in this case, I just copied it here so we can actually have a look at the UDF. So you actually use fashion. There are two UDFs here, and since this is all Python, so you just have the normal fashion clip class that you would have with that model, and the only thing that you really attach to it is this decorator, which kind of tells DQL, and also so therefore also DVCx, as DQL is just a library behind it. That this is supposed to be used as a UDF, and this can be used in queries, and it tells it how to use it in queries, like the one that we just made. So, for example, here I'm saying, okay, give me the fclip score from that model, do it in batches of 100, and initialize this model on each of the machines that it's going to run on. You can use pretty much anything, any kind of UDF that you can think of, and make it a part of your workflow here, make it in a parallelized fashion, on all of those machines. So then you can really do this at scale. Or instead of UDFs, you can use the stuff that's already included. We will include in the release, we will include some basic similarity search and stuff like that. So there will be some stuff that's included that's even more optimized and you don't have to write. But if you have something that's missing, you can always write a UDF and use it in your query to add to those signals. So now we could add those JSON pairs. We could add the scores from Fashion Clip or any other model, and then we would maybe version the data set and ship it. Maybe we want to do a bit more. Maybe we want to make it smaller. We just want to reduce it to some specific images. So you can just query as you would in something like Spark or SQL. You have, for example, a filter method, which is going to allow you to kind of zoom into something specific. So, for example, in this data set, I just take things which are large enough, and then they have let's say, this punt safe is kind of a measure of, is this maybe sort of like, as they say, not safe for work images. So I just deliberately picked those that have a high score. If we look at one of them, yeah, so it's like yoga. So apparently the model has some suspicion about this being something that is not safe for kids. and this one is even funnier, actually. It's just naked truth. So that's bad. So you can, if it's actually something that you want to filter out, you can get rid of this and keep only the stuff that you want to train on or that you want to use downstream. One other thing that you can do, if you have a specific image that maybe that your models don't work on, you can add similarity search, as I mentioned. So, for example, here again we can use Fashion Clip to just get things which are the most similar to one image, and again run all of this at scale. So for your entire data set, you just pick the most similar images. Here we're limiting to 20 just for demonstration purposes. So I have this, what is this image? I can show you that image, I think, that I used here. Yeah, so it's like a screenshot. So it's not really a picture of someone in clothes. It's like a screenshot from the website, and it's going to show me the most similar images. Yeah, so I don't know, this one. Yeah, so it's also a screenshot. So maybe I want to get rid of these, and I just want to keep people in clothes and not the entire eShop. So we can do all of these things like that. You can see that you can do all of this. You could do it without DVCx, but what DVCx adds here is the scalability and the way to combine at that scale of billions images, to combine all of that information into this metadata dataset that you can then reuse, that you can export and use downstream. The last thing I want to mention before we finish, because I'm running out of time, sadly, is delta updating. So you can also, as you add new, as I mentioned before, you can have this situation where the new collection comes in, right? So you want to update a data set, but you already have, I don't know, 50 million images, and now you have a million more. And you want to add all of these signals, from fashion clip. You want to pair the JSONs again, or it can be a lot more than just a fashion clip. You can have 10, 20 models. That's actually, in fact, that customer that I don't want to talk about directly, but they have something like this where they really have a lot of models that each kind of give a specific description of the images so they can sort them out. Their big problem is they don't want to do it on the entire data set all over, because that's even if you can do it relatively fast with concurrency, you don't want to waste the money and the compute resources to do that every time, right? If you have 50 new images added to a few billion. So you can actually use delta updating. Right now, it's actually sort of, let's say, a bit manual, where you kind of just query the old data set, you subtract the old from the new ones, and then you run all of these methods, like adding those signals only on the new one, then you put them all together. So that basically saves the resources. In the release, it's most likely going to be automatic, where you will have delta updating, and you will also have automatic reindexing as you add more stuff to the buckets. So you can then create and iterate new versions without actually having to remember to do all of this manually, to have people create those new data sets. Right, so that's basically it. So DVCx really, it kind of works as something like what you could do with something like BigQuery or some other methods, but it adds these extra features where you can create all these UDFs, create more context, more information, put together all of this metadata to your images, and create this finalized data set that you can then work with down the line. It will integrate well once it's released with DVC. So DVC will be able to import the results of DVCx and work with it down the line. And it handles a lot of the stuff that you would want to do about decoration, so it can handle that stuff automatically for you. All right, so I'll stop here and I'll have a look at the questions. Well, we have quite a lot.
Yeah, thank you for your presentation and the review. And it's really very similar by the interface to the BigQuery. So if you have some questions, please ask the question using Slander, and we will read these questions. You can find the link under the video, or you can scan this QR code and ask the question. First, I have also the question. As I understand, it's not possible to install on my own environment for free. It's not open source product.
That's a great question. Or
will be.
DQL. So I mentioned that we have DVCx and then we have DQL. So DQL is the library behind DVCx, but DQL is going to be open source. So you can run it in your environment, you can run it locally, but kind of the nature of the product is you can do it. So it's the same way that you can run Spark on your machine, usually you only want to do that for debugging or trying things out, because you want to run this on a cluster to really make advantage of all of the features. If you have something that fits on your machine and then you don't need to parallelize, then you probably don't need DVCx. So kind of that's the idea. So you can use DQL, you can test things, you can even develop, and then you just export it and you can use it with DVCx. to really upscale everything. But yeah, in order to use the concurrency and all of these automation tools, all these cron jobs and things like that I showed, and the UI itself, you would have to actually use the paid version.
Yeah, understand. One question we have about your switching from mathematics. Yeah, why you switch?
Yeah, that's a great question. Yeah, that would be for a longer talk, I guess. But and you're right. Göttingen is a great place to study mathematics. I'm not sure I actually mentioned that I was there, but I think maybe it was in my bio. But yeah, I mean, in mathematics, you really have to be either like top few percent in the world, or you kind of have to go where you find a job, where they offer you a long-term opportunity. And because it's, the academic market is a bit scarce in this regard. So that's one of the reasons where I decided, maybe I kind of don't want to go to, well, nothing against New Zealand, just as an example of a place that's far away. I don't want to go to New Zealand just because they offered me a position there, and I don't want to lose that. Yeah, so that was one of the reasons.
Yeah, in academia, it's sometimes you need to go to a new country, new institute, because only on that place you have some opportunity.
Yeah.
Yeah. So
I think there was another question in the chat. What's the name of the product you are promoting? Yeah, so maybe that was a bit confusing. So we have DVC is one product. That's a free open source software. That's the MLOps thing, kind of like the GitOps tool. There are other libraries related to it, but we kind of all just group it and call it DVC. And then there's the Studio, DVC Studio, which kind of puts together both DVC and DVCx. That's a paid product that you can use to kind of give for collaboration, and for especially with DVCx for all of this concurrency and all of these features that letting you upscale everything. And the DVCx is the new product that's not yet released, and that will be released probably in December, and will be included in DVC Studio. And that's the main thing that I was talking about. Yeah. How you generate embeddings of images? How long does it generate? Yeah. So that, how long? It really depends on how many images you have. Yeah, but I see, for 100 of millions of images. Okay, so it depends still on the cluster that you create. So if you create, like I said, I was not really running those queries because I'm in my account now limited to a single machine cluster. So things are relatively slow. That's really not the use case for DVCx. Instead, you would want to run, depending on how many images you have, you could scale it up to 10, 20, usually not that much more than that. It also depends, obviously, on how big those images are and how complex that algorithm is for your embeddings. So I can't really give you a precise number, but you can think of it this way. So if I have one machine, it's going to take me, let's say it's going to take me, when you were talking about 100 millions, realistically, it's going to take me 2 weeks, potentially, If instead, and that's the same if I just run it locally. But if instead I upscale to 20 machines, I'm going to have it done in less than a day, potentially. If I have GPU machines, it might be an hour, But obviously that's going to cost more. But if I want to iterate quickly, I don't want to wait 2 weeks between each iteration of my ML models that maybe depend on that data set. So it's the same as, in this regard, you can think of it the same as with Spark. If you run on a single machine, it's going to be slower, especially with a large data set. If it's a small data set, then maybe not. And if you have a large data set, you really want to scale it up.
Yeah. So I think thank you for this presentation. Thank you for both with us and share your knowledge and your product. To do some preview of your product, it's very cool that you share what you will release. Thank you for all who was with us today and who asked the questions. If you will have more questions, let's continue discuss in our Slack channel, and see you on the next webinar. Our next webinar.
All right. Thank you very much, and thank you for having me.
Yeah.
So, all right then.